Hello, everyone. Whether you're on YouTube or on Zoom Live, we welcome you to our monthly meeting on the data science side. We do several meetings, in a year, but especially, particularly on the data science side, and that's where we basically try to make sure that we get two meetings a year. First Monday and first Wednesday, third Monday and Wednesday of the year. I'm a little bit off on that one. We're really glad to have Jules Damji here presenting on scaling AI ML workloads with the Ray ecosystem. So Ray, you don't know this, but several years ago, I was invited to a Spark, actually a Databricks conference for some work that I was doing for my company, and it was really interesting because there were actually there was an expo along with it, and I saw some folks from UC Berkeley basically presenting their upcoming work and so on and so forth. So I was like, yeah, that's pretty interesting. What problem are you trying to solve, right? And there was a lot of collaboration with folks at Databricks as well. And um, that's really the first time that I actually heard of Ray. And since then, I haven't managed to keep up, completely, with the advances on that side. So a couple of months ago, when this topic came up, I was actually really excited that we'll be showcasing this to the audience that SFP ACM has a privilege of presenting to, right? More from a community development perspective. So welcome, and thank you very much for leading this conversation. Hopefully we have a lot of good questions from the folks who are attending here and on YouTube. So before we go ahead and get started, I'll just take a couple of minutes to go through what the San Francisco Bay Area chapter of ACM is all about. We've been around for over 60 plus years, 65 years, I guess. And ostensibly, right, our effort has been to really encourage the networking aspects, professional, skill development aspects, and other things of the computing community, particularly in the Bay Area. We do this through a number of things, through workshops, through talks like these, through networking events, and over the years and decades, actually, we have continued to evolve to support, a wider and wider range of community engagements, right, through meetups and in-person talks and other things. So in this respect, we are really privileged to have the support of many volunteers and the amount of effort it actually takes to run this, organically and in a sustainable way is not much, so every little bit actually does count and help. So there is a small, $20 annual membership. If you believe in the vision and mission of our chapter and for ACM, we would really appreciate it if you would consider doing your annual membership, getting an annual membership. And there's a number of privileges that basically come with it. We can talk offline. But in essence, the biggest one being that you get significant discounts on, workshops that we hold, several times a year. And that in itself pays for the membership through the discounts several fold over. So hopefully you consider it. We have 2 monthly meetings. The general computing topics are on the 3rd Wednesday of the month, and the data science topics are on the 4th Monday of the month. So that's what I was referencing earlier. And usually, we also have some announcements from the community, in terms of hiring, etc. If you're looking for a job, you can raise your hand. If you are looking for people to hire, you can raise your hand, let us know in chat. and we'd be happy to set aside some time for you to make your pitch, so to speak. So think about it as I go through, and before Jules takes over, we would love to give you the voice audio for a minute or two to talk about any hiring that you may be doing. And if you're looking for a job, then raise your hand and let us know as well what your background is. Okay, there we go. So today's so an upcoming topic for us is on limitations of AI systems on explainability, causality, and ethics by Dr. Alok Agarwal. So hopefully you'll be able to join us on the third Wednesday. Is it the third Wednesday? Yep, third Wednesday of the month, next month. Okay, so respecting the speaker, we will silent the audio for everyone who's not a panelist. However, we definitely do encourage an interactive session. Please put your questions in chat, and we can open up the mic for you, or we can relay your question to the speaker on your behalf. So please let us know whichever way it works for you, and we hope that it will be very interactive for you. The topic of scaling ML/AI workloads with the Ray ecosystem is really, to deep dive on the Ray architecture and the why and what of it, right? So I'm not going to read through the entire abstract. Hopefully you read it before you came here. But if you think about the development of machine learning and AI algorithms in particular, right, the challenge of putting it into production, scaling it, has been one of the biggest ones, right? So without you having to get a separate degree in, DevOps and spending years on an ever-changing, very rapidly changing field, things like Ray basically help us, overcome many such challenges of parallelism and cluster level deployment. And it actually helps to know that Ray is actually open source, right? And there's a lot of other efforts as well that are looking to consolidate, within, closed environments, right? So it's nice to see that Ray is open source, taking contributions from a number of places, and really looking forward to Jules talking more about it, right? And so, Jules, I would also say that as I see this, I see about 10 different companies in the AI ML space that's already incorporated it to Ray, right? And the fact that it comes out of a university environment, and it attacks and addresses a very distinctive series of industry problems, really just speaks volumes about how useful this research actually has been. So thank you. Jules is a lead developer and advocate at Anyscale. He is a co-author of Learning Spark. Hopefully you've seen the book from O'Reilly. Just before this, we were actually chatting a little bit about some of the background and how he came to write the second edition. Looks like Spark has actually gone through tremendous evolution in the last 7 or 8 years or so. And so it's really great, Jules, that you were able to incorporate a lot of that into the second edition. We also spoke a little bit about his background, right? So he has an MSc in computer science, but in parallel, he's managed to get a master's in political advocacy and communication. So extremely impressive background, broad knowledge base, and I would say, Jules, especially as ethics in AI research and other things become more and more prominent, I feel that folks like you who have a toe or a foot in multiple disciplines, right? Only can serve us better. So thank you. Before I hand off to Jules, I would like to just take a minute, pause, and ask: are there any opens and any announcements from community, from attendees?
And you can, if you're an attendee and you have such an announcement, you can raise your hand and we'll recognize you. don't see any raised hands at this point.
All right. Well, that's great then. We will then go ahead and hand the floor off to you, Jules.
Okay. First and foremost, I really want to thank ACM to invite me with this at this particular meeting. I've spoken at the ACM chapter in Chicago. Was really honored to be there as a guest of Michael Franklin, who was one of the co-founders and the director of AmpLab, where Spark was born. And coming and giving a talk over here is actually a really honor and privilege. So I do want to thank the ACM chapter to invite me. So I feel quite honored to be sharing what it means today to scale AI and ML workloads using this new Ray ecosystem, which is the open source library was built at UC Berkeley. As Yahesh pointed out, I'm Jules Damji. I'm a lead developer at Advocate, so I'm not going to go into my who am I? Proud to be a co-author of this particular book. It sort of covers all the 2.0 and the evolution of Spark, the 2.0, the 3.0, and the Delta Lake and ML flow. So I was really honored to be part to write this book along with my co-authors. So that's who am I? And I think Ash wanted to point out how did I actually end up being a developer advocate? And I thought I would share this particular little anecdote. You know, after being an engineer for almost 20, 25, 30 years, I had a moment of epiphany whereby I said, I really enjoy writing code, but also enjoy writing and connecting with people. And so what should I actually do that I can combine those two skills? And I was an absolute introvert. I just could not even speak at the meetings. I could not give public talks at all. I was literally one of those quintessential introverts who would just sit and write code and not interact. But inside me, I had this growing feeling that I need to connect. And so one day I was working for a startup company and I left and went to Washington, DC. And my wife was wondering what the hell is going on. Are you having midlife crisis? And I said, consider that mid-career crisis. I want to go study communication so I can actually really go into this particular field of advocacy because I felt very passionate about conveying and communicating and sharing knowledge. So I went to study political advocacy and communication at what other place in Washington, DC, which is the heart and soul of political debate. So I was there for 2 years and I was trained to be a speechwriter and also a spokesperson. And when I was sitting in the Washington, DC writing and press releases or writing speeches for my professor, he said, I think you should go back to the Silicon Valley and use your particular skill because you hate politics. And I said, yes, thank God for reading my mind. So I returned back to Silicon Valley and my first job was as a lead developer advocate at Hortonworks. And then I went to be a lead advocate at Databricks and the rest was history. So I found my niche, I found my calling, and that's how the transition happened. So you got the story, Ash. Okay, so who do I work for? So I thought, I already told who am I, and I think it's important to get the context of the company I work for. So we are the original creators of Ray, which is the open source project that I'm going to talk about today. And just like any other open source product, there's always a company behind that actually provides sort of the managed service for compute platform. And this allows us to be able to actually use that where you don't have to worry about cluster management, you don't have to worry about scaling and upscaling. We actually manage all that for you by providing a managed service on the Anyscale platform. But I think the most important thing is that why? Why do you think it's actually important? And we feel that scaling is a necessity today. We are entering what I would call the zeitgeist of AI and ML. And scaling is hard. Distributed computing has been going on for the last 20, 30 years. And we have realized how difficult it is for it to really get it right, to make sure that it's a lot easier. And our goal of a moonshot vision, if I would call it, is to make sure that distributed computing is easy and simple for everyone. Just like at my previous employer, our mission was to make big data simple with Spark. And over here, our mission really is to make distributed computing simple and easy. So any Python programmer doesn't have to have a PhD in computer science or mathematics or distributed computing to understand how things are actually working. They just write Python code and Ray and the underlying toolkit or the underlying compute infrastructure takes care of that. So that's what Anyscale is. So why are you here today and what am I going to share with you today? So I want to take you on a journey. I want to take you on a journey starting from a very high level, 20,000 feet of why Ray? What were the motivations behind it? What inspired people at UC Berkeley to come up with this new, yet another distributed system? What the Ray ecosystem looks like. And then we'll descend down to about 10,000 feet. Well, I'll go behind the scenes to talk about what the Ray architecture is, what are its components, how they work together, because I think it's important to have that insight. It's one thing to drive Aston Martin, another thing to open the bonnet and look at what's underneath. So I think it's important to understand those components. And then we'll go down all the way to the zero level above sea level, where we talk about the Ray core APIs, the design patterns that make this distributed computing a lot easier. And then I'll talk about one of the libraries, which among data scientists or among ML engineers who are here today will realize that they do tuning quite a bit. Hyperparameter optimization is an imperative part of your machine learning lifecycle. And among training, you actually do tuning quite a bit. And so I'm going to concentrate on that particular one of the libraries. We have a few other ones. And hopefully I'll get a chance to show that as a demo where we scale 3 different workloads, how to train a particular model, how to tune it, both locally and then on a distributed machine, how to do inference in both cases. And you'll see a noticeable time difference in all of them. And then hopefully we'll have lots of Q&A that I can participate in. If for the questions and answers I don't have, I'll definitely go offline and we can connect. And as Henry Kissinger would end his press conference saying, I hope you have questions for prepared answers. So just kidding. Okay, so why Ray? I think that's an important question a lot of people ask today. Why do we need another distributed system? We got Dask, we got Spark, we had Hadoop. Why do we actually need that? I think when the creators of Ray at the time in UC Berkeley, when they were actually looking at the trends, they were very prescient in assessing that the 3 industrial pervasive trends which are actually going to dominate in the next decade or so. And one was they already betted on the fact that machine learning was going to be very pervasive in each and every domain, in the vertical domain across the industry. And so that was the first sort of industry trend that they betted on. And as a result of these particular machine learning being pervasive across all sectors, distributed computing machine learning was a necessity. It wasn't an exception, it wasn't a norm, it was going to be a necessity, because in order for things to be pervasive in a distributed manner, you actually have to have this a toolkit that allows you to do that at scale. And last but not least, and I think I would be at loss if I didn't say that the Python is the default language of data science and ML. If you go to any of the conferences today, Python is at the center if you're actually doing that. So let's look at the first trend, why machine learning is actually pervasive. Now, if you look at this architecture diagram, it is obvious that today people are actually building large and very sophisticated models using lots of data and scaling this model across clusters in all these industries. You got finance, which are actually doing fraud detection. They are doing forecasting. They're doing stock trading predictions using these very sophisticated models. Needless to say, smart automation has completely revolutionized how the auto industry is working, both in autonomous driving and also in drones, how they're actually using computer vision to navigate through different ways. There are some nefarious uses of it, but I think in general, there's good bits of it. AI in healthcare has actually made a tremendous impact. And over here, the models we are doing the simulations that are doing in protein and drug discovery is enormous. And they're all required for you to be able to do simulations at scale. Manufacturing has taken a huge impact on how robots are actually doing it. AI industry, for example, in the hospitality services, we have recommendation systems that actually pretty much recommend you where you should go, what you should do, and all these are industries in which these models are being built at a massive scale, and as a result of that, things have to scale. And it's because it's blessings of scale. I like to call them blessings of scale, which is a term that I actually borrowed from The Economist, which had a very good piece on the frontiers of where AI is heading. And they plucked this particular chart from one of the archive papers, and it actually speaks volumes here. It speaks volumes because if you look at the trend over the past 30 or 40 years or 50 years, we have seen the models, the language models being developed are getting more and more huge, again, more and more sophisticated. And today's foundational models, if you look at the upper far right, do require a fair amount of compute power. You know, the floating point operations, which are happening at low scale, is enormous, right? You can do your computing on your laptop about, you know, tens of billions of instructions per second. But when it comes to building these foundational models, you really actually have to embrace the blessings of scale. And that's where this whole idea of blessings of scale comes across, as this particular diagram shows. But at the same time, you know, the blessings of scale also introduce its counterpart, which is, you know, there is definitely a compute demand supply problem. Now, some of us who are here today may not be sort of building models at the scale of, say, Manga, right? Where they're using all these language models to build that. But I think over a period of time, you will see that more and more people will be actually using these large language models which are being developed. And it turns out that there is a shortage in terms of how much you can actually use the compute power, right? The CPU, the Moore's law is over. The CPU has fallen short in terms of the number of petaflops you actually need per day to train this model, you know, to inference this model, to test these models. And you can see there's a linear exponential curve of every 35 months, this model's actually growing. And even though arguably the hardware accelerators do provide a certain mitigation of that, the GPUs and GPUs that have the same trend, but there is still a fundamental gap that's actually missing. And our contention, or the contention of the researchers at the time when they were thinking and conceiving what should be the new framework that we developed, was we have to distribute at scale. There was no way out, but we have to distribute that particular scale. And that sort of was the necessity that actually emerged out of the first trend, which was machine learning is going to be pervasive. And in order for it to be pervasive, we have to distributed computing has to be a necessity and a norm, and not an exception. And finally, last but not third list, we know, and those of you who are here also can attest to the fact that if you are a data scientist or an ML, you're invariably, you know, working on one of these PyData ecosystems. There's a reason why we have so much thriving community for the PyData and PyCon. If you actually attended any of the PyCon conferences, if you attend any of the PyData, you know, all these things are flourishing. People are actually using this, and most of them are either data scientists or statisticians that are using it. If you're sort of involved in doing deep learning or ML specific tasks, you're most probably using these libraries on the right-hand side, and each of them have a Python binding. So it's fair to say, and I think it's sort of become more of an axiom, that Python data science ecosystem is dominating, and Python is the de facto lingua franca of this particular nature. So that sort of says why they were thinking of Ray at that particular time. And I think it's important also to think about what were the academic researchers and the origins of Ray, how it actually happened. And so during the time in 2009, at the time, AmpLab was about to close down and RISELab was opening. Professor Owen Stoica, a prominent figure in the UC Berkeley Computer Science Department, and also a prominent figure in the AmpLab and RISELab, is one of the directors of RISELab. He and David Patterson, who was a known award winner in the computer science department, sort of wrote this particular blog, which we turned into a paper, where they were very opinionated about sort of saying above the cloud. You know, this was a Berkeley vision of what the cloud is going to look like. And they published this particular blog and paper in 2009, and it generated quite a bit of fervor in the academic industry. And there were about 17,000 citations just used in this particular paper. And 10 years up to date from that particular paper was released, there was another paper that was actually produced or released at that time called Serverless Computing. And it, like its predecessor, was very opinionated, and they had the idea about what the future of computing is going to be like. And so there was this postdoctoral student called Eric Jonas, who did some research and realized at RISELab that most of the graduate students who were there were not using Spark to doing the machine learning workloads. All they were doing was they were actually working on their particular laptop, their Python code, and then whenever they actually needed something to scale, they would just connect that to a particular cluster and then run the workloads over there. And at that time, the computing, I mean, the cloud computing had really taken off, right? And there were three sort of observations that articulated in this particular paper. One was that this whole notion of decoupling the computation and storage, where the students can actually just write whatever code they want on the particular machine and then run it on the cluster and don't worry about where the storage is and don't worry about how much compute they need. They just wanted to decouple that, so they're not worried about, I'm just going to write this particular function, or I'm going to write this training function, I'm going to run it in a distributed manner, and I'll figure out, I'll create the cluster that I need. So that was sort of the first observation of the paper. The second one, which was very prescient, was that the whole abstraction behind coming up with any way to write those functions would be to be able to take that particular code that you actually have and have it executed anywhere on the particular cluster and only pay for the amount of compute that actually need. And this abstraction was something that actually played quite a big role in the emergence of Ray. And finally, the third one was that they didn't have to worry about paying anything, right? In terms of they only pay for the code of execution, which was either small or which was large, depending on how complicated their task was. And they wouldn't have to worry about allocating the resources. The infrastructure would actually take care of that. And that was sort of the whole notion about serverless computing. And this kind of led into really the outcome of what Ray was going to be. The collective ideas and the collective brainstorming at the time of RISELab really led to the emergence of this particular new distributed framework that allows you to compute your Python code or your ML workloads across the cluster. And so the origins of Ray really go back to these really notable, I would call it, crucibles of innovation, right? These are the centers of innovation at Berkeley. Ampleg created Spark and Mesos and Caffe. And then 10 years after that, you had Ray coming from sort of the same researchers in Berkeley. And that's how sort of the origins of Ray emerged to address today's demands about scaling and doing computing ML at scale. So that was the origins, right? I talked about the three trends. I talked about what were the academic origins that actually prompted people to think about this new distributed computing framework. And so now I want to talk about what Ray is all about, right? What is Ray? And you can think of it, Ray, as a simple, just general purpose library to write distributed computing, right? And I think the important part is that general purpose, right? It's a very universal general purpose library that allows you to write scalable distributed computing, take your Python and convert that into a distributed fashion. And you don't have to worry and learn a lot about distributed computing. It does all the hard work for you. You just write the code for you to do that. It comes straight out of the box with an ecosystem of Python libraries, for scaling your typical machine learning work and any other Python codes that you actually have. And last but not least, it can run on your laptop, right? Which is an important bit of it, because today a lot of people actually build things on the laptop, whether they're running on a MacBook, whether they're running a laptop, whether they're running an IDE or whatever VR, Emacs, however it is, they run on a laptop. You can run it in a public cloud by just connecting to the Ray cluster. You can run on Kubernetes. You can run on on-premise. So I think there is this flexibility of what that is. And I, being a visual person, I like to think of it as a layered cake of functionality and capabilities for scaling your machine workloads. So if I had to sort of build that particular layer and show you what it looks like, it would be something similar to, at the bottom layer, you have all the public clouds and all the places where the infrastructure can run, on AWS and Azure, on Google and Kubernetes, and on your prem, so it can actually run anywhere. And it's a universal framework, and I think that's the important bit about that. What I mean by universal framework is that it's not built on any sort of data structure, like say a data frame or a Dask DAGs, and providing you a DSL on top of that. It's actually built by providing you with some core primitive APIs that you can actually use to write distributed computing. And you, as a user or as a developer, we'd not have to worry about how it's going to scale, right? What is going to be my memory management, or where is going to be scheduled on the cluster, how the performance is going to be. You don't worry about let Ray take care of the hard bit. It provides you with APIs for you to actually write that. And I think if I could actually use this analogy, and this might be a bit far-fetched, but I'm probably dating myself by saying this. When you think about early days when Unix was developed, right? When Cunningham and Ritchie and Ken Thompson were thinking about the PDP-11 Bell Labs, the first origins of the Unix system, they thought about abstracting the operating system, all the operating system, the scheduling and context switching and threading, all that away at the operating system level, the kernel level. And they provided the simple primitive APIs for you to actually write those applications, right? So you had this abstraction called file descriptor, and a file descriptor could be anything, right? It could be a pipe, it could be a network socket connection, it could be a device driver, it could be a window manager, it could be any one of those things. And you had APIs like, do a get, do a put, do a write, open. These were the primitives. And then what happened, right? People started building applications on top of that. And as a result of that, you had the proliferation of all these applications today and systems that have actually been written on the fundamental of those primitive APIs. And so if I extend that analogy and I say, okay, if you go up one level on the Ray layered cake of functionality, on the left-hand side, you actually have this primitive, this ecosystem, the native libraries that we actually provide, which are built using the Ray primitives that allow you to do this distributed computing. So you're using those libraries to scale your workloads. You don't have to worry about, oh, where am I doing my fopen, or where am I doing my context switching, or how am I doing threading? All that is taken care of by the underlying system. You just write the APIs, write to the APIs and write your applications. In the middle layer, similarly, these are the ecosystem libraries that are integrated with Ray and work very closely with Ray. So it provides you an ecosystem to do that. And on the far right, on the upper right corner, if you don't care about machine learning, right? If you're just a Python programmer who's doing some simulation, or you want to do some high PC and you want to scale your Python program, you write those particular primitives to be able to actually scale your infrastructure at scale. So that's sort of the layered cake of functionality that I was talking about. That's what Ray is all about. And as I say, right out of the box, when you use those native libraries, you can use any of these libraries which come straight out of the box to do any of the workloads that you actually want to do. So if you want to do your last mile data ingestion for you actually training the model, you can actually use the Ray datasets to be able to do your pre-processing, to be able to do your mile ingestion, to be able to use any of these integrated libraries with modern by using this particular Ray datasets as part of the Ray core. If you're training, right, you want to do distributed training, you can actually use PyTorch along with Ray to do your distributed training. And if you have models that are actually being served, you can actually use Ray serve. And those of you who are building models and trying different trials, you can use the straight out of the box called Ray Tune that supports all these sort of algorithms that are out there, along with the schedulers that work with it. And you can also use the hyperport and Optuna along with that. And if you're in reinforcement learning and you're solving gaming problems, you're solving decision making, if you're solving operational problems in real time, or you're actually building agents that allow you to make these decisions, then reinforcement learning RL library is one of your libraries you can actually use. Now, the good thing about it is that you can use one of them, or you can use all of them together. It's not one or all. You actually have the ability to use one and chuck the other ones if you like. So that's sort of the beauty of these particular library, which actually can work together, but also can work independently. And so who are the companies who are using it? And I think Yayesh mentioned that he had read about all these different companies who are actually using these Ray at a massive scale in production already. And if you want to exactly find out, we don't have time to talk about all the user stories and how they're using it, but you can go to ray.io and actually find out exactly how they're using it, what they're using it for. And they have this various different myriad use cases that Ray actually addresses using all the libraries that I talked about. And so that essentially sort of talks about what Ray is and what are the motivations behind it and where we are today and who is actually using it. So before I move into the next section, I just want to pause here for a second and see if there are any questions that people might have for what I've talked about in terms of motivations, in terms of what were the origins, what were the driving factors that led to the creation of Ray.
At this time, I don't see any questions in Q&A or chat.
Brilliant. Okay. So let me just move on then to the next section, which is the array architecture and the components, right? Now I'm just going to descend down a little bit and talk about what is the anatomy of a particular array cluster. Now, those of you who have been working in distributed computing, this particular diagram is not something, is not novel. You look at a Dask architecture, it looks very similar. You look at a Spark architecture, it looks very similar. If you look at Hadoop, for example, it's not very dissimilar. They all sort of have the same idea that you actually have a head node, which has a central place where workers are running. You have then worker nodes that actually do the computation, and they share things among each other. There are a few distinctive things about array architecture which makes it unique. One is that you have these worker processes which are tied to each and every core. So if you actually have a worker node that has 16 cores, you will have 16 worker processes that you can actually create on those. And each of these worker nodes, they have a very unique process called RLlib. And RLlib has two threads. One is a scheduler and one is an object store. An object store is a plasma object store shared memory that local tasks which are scheduled on it can store data in it or can get data on it. And these RLlib talk to each other throughout the duration of the lifetime of a particular cluster. So they exactly know each other, where things are running, who is running, who's got what resources, what objects are stored where. So they have a very sort of what I would call a distributed scheduling that's quite unique to Array. And then on the head node, you actually have a driver, and just by convention, we actually have driver running on the head node, but it's not necessarily a head node driver can run anywhere. And there's another process called global control store, which actually is like the meta store that has the information, the state of the information of the cluster, who is running what processes, who is running what task, who has what GPUs and what resources, what code has been executed where, and here is the metadata associated with that. So this is like the global store. And if I go one level below to see how these things work, when you create a particular task, and we'll get into what tasks are and actors, they get scheduled to run on a particular actor. And they are bound to a particular worker. You can actually have many tasks running on those workers, and that gives you the ability to run and fan out, tasks across all its workers. There's a RLlib that actually talks across each other and transfer objects if there's actually needed from the object store, and they'll communicate all the time with the global central store that actually does and maintain the state of the state of execution, so to speak, the heartbeats and all that. And all that's actually very fast and efficient using gRPC, happens very quickly, and you won't even notice when you actually do a task, everything is actually done. But that's sort of the beauty of having a distributed scheduler and having a distributed object store, which is an important part of scaling, because this is quite unique to Array. So that sort of is at a high level of what are some of the components, how they work, why is it actually important to have a distributed store so you can actually share objects across. Especially when you have tasks which are running on a particular worker, they can actually just use zero copy to get the values of any objects that might have been created during the task. So that way, there's no IPC or there's no network connectivity if they are scheduled on the same task. So this is sort of behind the scenes. The next thing I want to
Jules?
Go ahead. Yes.
There was a question that came up here. Greg, did you want to unmute yourself and ask that question? Or I can read it out here. Let's see.
Isn't it in the chat?
It is in the chat. What NVIDIA support train on a cluster like 8 GPUs or more?
So all the NVIDIA TLS GPUs, we actually support those. Right. So if you actually create a particular cluster on AWS or on Azure, and you can define what NVIDIA GPUs actually need, those hardware accelerators we do support. So you can actually create a cluster with 8 GPUs, and now you can actually use 8 GPUs. And those are the NVIDIA clusters, NVIDIA GPUs that we actually support.
Okay, Greg, hopefully that answers your question. Okay, thank you, Jules.
You're welcome. Yeah. Okay, so now I want to talk about, dropping down to a more zero-level secret. What are some of the distributed design patterns that Ray actually uses, the Ray APIs? And those of you who are software engineers have sort of come across this design patterns, right? There are some design patterns in programming languages, in architectures, in object-oriented language that were introduced by this Gengo 4 in this really companion seminal book. And Ray actually has 3 design patterns that allow you to write these distributed applications seamlessly. One is there's this notion of Ray parallel tasks. And these are functions that you can actually, Python functions, you can actually take and convert them into stateless units of execution, right? Very easily. These are stateless and they can be executed and scheduled anywhere in the cluster. The second design pattern is the Ray object store or Ray objects, which are futures really. And those of you come from the C++ or Scala or C# know what futures are. Those are entities or objects which are created for you that will hold some value in the future. And those are sort of asynchronous in nature. So I can actually create a particular feature and return you a reference to it. And then later on, I can actually find out what the state of that particular feature is. And this enables Ray to be able to fan out tasks at a massive scale. And if the tasks return a particular value, they'll just return you an object, but then continue executing and then eventually fill the object that you can actually fetch using one of the primitives to do that. And then finally, the counterpart to Ray parallel tasks, which are stateless, you have Ray actors. And those of you are familiar with actors, kind of a similar idea where you actually have a stateful service on a particular cluster that you can actually take your particular existing class that you might have and convert that into a distributed manner as a stateful service to which you can send messages by invoking its class methods. Very Pythonic in nature that way. And there are some links over here for those of you who want to know what are some of the patterns of parallel programming that we're going to incorporate over here. You actually see that there are very specific Ray design patterns that we actually have. These are some of the 3 ones that I wanted to introduce you. There are other ones that are available in that particular link, and how some of the libraries are integrated using these particular design patterns. And I'm going to share this PDF version of the slide with Yash, and you can actually share that with the rest of you. So let's look at what it looks like, right? So I have a Python functions on my left-hand side. I have a function, I have a class, and then I'm creating some particular objects. And I want to convert them into array settings so that they could be scheduled on a distributed manner. So what I do is I use the Ray decorator as one of the design patterns on top of my particular function. And when I do that, when you actually execute that particular function, this is going to be distributed as a function anywhere in the particular node, right? This is going to be converted into a stateless task and will be scheduled on an array cluster. Similarly, if I have a class, I can take a particular class and just include the Ray.remote decorator, and this now is going to be converted into or attached to a Ray worker and converted into a class. And once I have an instance of that particular class, I can actually invoke any of its methods, just like I would invoke a class method, and it would do the RPC call and return a value as an object reference, and you can actually always get that later on as a feature. And last but not least, you actually have what we call the distributed immutable object store, where you can create massive objects, and by just doing a Ray.put of that particular object, what you're doing is you're actually putting this particular object on some location, on some node in its plasma store called Ray, object store. And this could be copied over to another node if that particular object A is required by another task over there. It copies over. If this task is scheduled on the same node, then there's no need to, because I can use zero copy to get it from the shared memory. So that's what the APIs are. Very simple, 3 or 4 APIs, and you pretty much can write your distributed application very easily. So that was sort of the Ray Python APIs. Now let's look at some more detailed version of what these actually look like. So I can actually have any arbitrary function called read array that takes in the path of a file, does read that array, converts that into numpy, and then returns value A, right? I can have an add function that actually takes two numpy arrays and adds them together and returns the value. Very Pythonic. You know, the only difference is that I have not converted that into a remote setting. And when I use that in the Python code, you can see that I'm just using read.array as my function. Oops. I'm reading read.array as my function, and I'm just using the .remote and then providing that. So .remote now is saying, go ahead and invoke this function remote and then return me the value. And it's not going to block at this time because it returns a future called ID1. And I can use the second function, returns me an ID2. And I can just send those references or those object references or those futures to my add function. And it will resolve within the add function saying, okay, this particularly is an object reference, so I need to find out whether it's actually done. It will try to do array.get. If it's done, I'll get the value, it'll resolve it, and then return you the value. And then finally, when I get the value called ID, I want to now, actually, it's a future, so I'm going to do a resolve of that. I want to find out what the value is. So I can do array.get on that particular object. And at this point, it might block or it might not block because the task add has already been done. And likewise, on my right-hand side, I can actually have a class that actually uses a decorator, and then I can provide my resources that I want. So supposing if I want this particular counter or this particular class to use, you know, 1 GPU or to use 2 GPUs or to use a fraction of a GPU, or if I have a runtime environment that I want some pip packages to be installed only for that particular function, I can provide the runtime environment there, and wherever this actually scheduled, it will go ahead and execute and install your packages. And this is just a class. All it does is sort of, you know, keep a state of a counter. And the way you use it is no different from how you actually would use a class instance. You create using the class called remote, and that gives you an instance, a handle to that. And then you just use the handle to invoke its method using the remote suffix. And that too just returns you a reference. Everything sort of returned by any particular task or an actor method is normally a reference or an object or a future that's going to be returned to you or that can be fetched later on. So this is what it might look like. You know, if I do a read.array, the first function could be scheduled on a node 1. The second one could be on a node 2, and it's going to sort of build this class or build this graph eagerly and interactively, very dynamically done. And then the third one might be somewhere in a node 3, and it's going to resolve those particular references and then get you the value back. And that's where the object reference come in. And when I do array.get, it's going to block and then return me the value if it's available. If it's not, then it will wait till that particular function is finished. So that's sort of the idea behind taking very simple functions that you actually have, taking classes that you have, and then converting them into a remote setting and just executing those functions, and you don't worry about how things are actually executed. Everything is scheduled for you automatically. You just write Python code and does things for you. The last, but the third one is the immutable object store that I talked about. And over here, you know, you have these worker processes on which the tasks are attached or scheduled, or a class might be attached to it, and they can, you know, run and create values. And when they return the value, what happens at that point is an object reference is created and it's stored in that particular memory. Now, if your object that you actually created is more than 100 kilobytes, then it's going to be stored in the shared memory. But if it's not, then it's going to be in memory, so that if you call next time, you can actually get it straight from the in-memory or transfer across to the next worker using gRPC. If it's a larger value and the second worker process actually needs the value of Y, it's going to get directly using zero copy. So there's not that much of transfer happening. And for shared memory objects that get filled up over a period of time, because you're creating a lot of objects that you actually have on that particular node, they get spilled over into the object store, and the references and where they're stored is normally handled and kept by, remember I talked about the global control store that has the state of the entire cluster at any point in time, so people know what object is stored where, who is executing what task, the serialized version of the task, everything is actually stored in there. So that sort of is the distributed mutable object store. And I think the important bit to talk about here is that if you have this particular code that's actually running on on node 1 and you're creating a function, you have a function f that's returning a value. You might have a function y or a function g that's returning another value, and you're sending, g a reference to an IDX. And at this point, g is going to be sort of scheduled on a node 2 because of the data locality. So here f is actually scheduled node 1. It's going to return a value. It's going to store that in its shared memory. And when G is scheduled, what happens is that now G is going to be scheduled on that particular node because the RLlib knows that the function X was scheduled on node 2. The variable X is stored in the shared memory. Instead of me scheduling that on another node, I'm just going to do it on the same node for data locality. And that way I don't have to transfer my X all over the place. I can just do that easily. So that's where the distributed object store comes into play. And how RAID tasks are scheduled, very simple. Actually, for example, if I have a remote RAID task that I actually want to schedule, what it does that the driver looks at the local RLlib and they say, listen, I want to schedule this particular task. Do you have the GPU or do you have the CPU resources to need? And it will say, yes, I do have, and I'll create a list for you. And once I create a list for you, I'm going to give you that particular list. The next time you need same kind of resources, you can just schedule that on that particular Python worker. And that's how sort of the RLlib comes into play. And it caches all these. So next time it has an idea of, oh, this particular task needs X amount of GPUs, and I know where it is. So I'm going to schedule it. It has these variables stored there. I'm just going to go ahead and do that. So that's at the very high level how the scheduling is done. But it uses all these different kinds of policies underneath the hood to make it more efficient.
So, Jules?
Yes, I'm going to pause here for the question before I go into the second bit, the last bit.
Okay, good. Thank you. I hope I was not breaking the wrong time here, but one participant, Pradeep, is asked whether there is a comparison doc or web resource to compare between Ray and Spark.
Good question. I think this is a question that a guy get asked every time, and my question, my answer to that is both figuratively speaking or metaphorically speaking, but also technically speaking. So when I get answered the question, I tell, supposing I was explaining that to my grandma about what is Spark and what's the difference in Spark and Ray. And I would say, Grandma, you got two beautiful children. You got Julie and you got Jules, right? And Julie is very good at doing things that Jules isn't. And Jules is very good at doing things that Julie isn't. But you love them equally, and they both are useful in the grand scheme of things. So if I take that to the technical level, I can say the difference between Spark and Ray is not so much that they are competing with each other. In fact, they are extremely complementary to each other. Spark is phenomenally great at doing data processing at scale, right? If I was going to building an ETL, and if I was doing data processing at scale, and if I was building my Delta Lake, and if I was doing structured streaming, or if I had a workload that was SQL load, or if I had a workload that was structured streaming, I would not even think about Ray, right? I would think about using Spark. On the other hand, if I was using massive distributed computing for hyperparameter optimization, I would use Ray because of the built-in ecosystem that it has. If I was doing reinforcement learning, I wouldn't use Spark. I would actually use Ray. If I was doing training in a distributed manner with PyTorch or with TensorFlow with XGBoost, I would use Spark. I mean, I would use Ray because it has these capabilities to distribute at massive scale. So both are extremely complementary and both work together well in the grand scheme of big data and ML. Now, comparing Spark and Ray would be like comparing apple and oranges because they both are distributed system, but they are unique in their own ways because they address different workloads. And you can't compare the SQL workload on Spark against an SQL workload on Ray because it doesn't exist. So there's no point of comparison, right? But my answer would be that they are extremely complementary, and there's no such document that compares those two because it doesn't make sense to do that.
And Jules, a follow-up question.
Mm.
What about torch distributed and Horoward? With
Okay, so the torch distributed and Horoward distributed and TensorFlow distributed is implemented on top of Ray is that we don't actually do the distributed computing itself, right? We provide you the orchestration using Ray actors, whereby we actually create the trials, the training function you actually need, and the inter-process communication is done by the underlying PyTorch protocols, right? So if they're using DDP protocol, they would actually use that. In TensorFlow, it might be using tfconfig to actually do the distributing. So we don't distribute it for them. We create the training function on a distributed function using Ray actor, and they do the automatic gradient synchronization. So there's nothing that we actually add to it, but we do the synchronization at a massive scale. And the underlying PyTorch distributed protocol and underlying TensorFlow distributed protocol is unchanged. It actually uses the same, right? So if XGBoost is using Rabbit to do all their gradient synchronization, we don't go and change that. We actually create the actors, then launch those trials in parallel, and then let the internal communication actually do using Rabbit or whatever the communication protocol is.
So for the learners on the call today, Jules, I mean, oftentimes, Minikube is actually used to basically, learn the innards of Kubernetes and other things. Is there a hello world type of, scenario that you can point folks to it by way of reference that allows them to use Ray on top of PyTorch distributed with maybe a Minikube set up on their laptop to basically see, how the APIs basically work together and get a functional,
Oh, definitely. I'll provide some Ray. I'll provide you with some code examples. If you actually just go to ray.io and look at the libraries, and if you look at PyTorch, you'll see examples where we actually show you exactly how to use distributed training using that, and you can actually do that on a laptop. But if you actually had to have run it on AWS cluster, if you have the accounts, you can actually do that. Yeah, we have all kinds of examples in our Ray docs. And I'll point you those to at the end.
Thank you. Please carry on.
Okay, brilliant. We got half an hour, so let me just run through this very quickly. So I'm going to now dive into one of the libraries that are very commonly used across the board by data scientists to do tune, right? If you're going to create a particular model, you might just train it for once using the default parameters that you have. But then later on, what about if you actually want the best model? And how do you actually get the best model? You're going to tune it. You're going to run several trials to be able to do that. And so that's what Ray Tune is all about, right? It is a library that actually comes straight out of the box with very efficient SOTA algorithms that allow you to run your trials in parallel, right? So I mean, if you're using the recent search algorithms that you actually want to use, that comes out straight out of the box, you can actually use that. And you can use that with their respective schedulers. So if I'm using, say, Bayesian optimization for my search, and I want to use, say, Asha as my scheduler to do early stopping or to do successive halving, then I can just select the algorithm, provide that in the Tune API, and I go off to my tracks. Because it runs on top of the Ray, we have a very effective way that Tune can orchestrate your distributed trials. So whether they are fault tolerant, you don't have to worry about that. Ray will take care of any failed trials by checkpointing. So because it runs on Ray, you actually get the fault tolerance. And because it runs on Ray, you can actually run it on your laptop, or you can run it in a single process, or you can run it on a multi-process, on a multi-GPU across the cluster, or you can run it on a multi-node, right? So the flexibility you have of how extensively you actually want to scale, you can actually use the train API. And the train API is very simple, right? You create your loss objective function that you want to train over. You provide your config hyperparameter space, and you say go ahead and tune it, and it will launch the number of trials you have specified, and each trial will get a slice of the configuration, and it will start tuning on that. And it works with all the libraries that you can actually use to write your training functions. If it's XGBoost, if it's scikit-learn, if it's PyTorch, TensorFlow, Keras, we support all that. You can write your regular training function that you actually have and then just put in your tune along with the config space, and off you go to the tracks. So because it uses sort of these combination of schedulers which actually are smart, you can actually use strategies like early stopping. So for bad trials, that way you can minimize a particular cost. Or if you're using spot instances, they might disappear. So then what happens, we do checkpointing on regular basis, so we can restore from the checkpoint and continue doing new trials. So it is quite effective in those particular areas. And as I said, these are all the algorithms that we actually support, the search algorithms, and all you do is just provide the name of that algorithm along with the compatible scheduler, and you just provide that as a name in the argument and run the tune, and it does all that automatically for you behind the scenes. You don't have to worry about it. For those of you who actually might be new to hyperparameters, I thought I would just sort of quickly distinguish and differentiate between the two. Hyperparameter is something that you set before the training, right? So those could be, for example, the kind of your neural network model architecture they might have. This might be your learning rate that you actually might have. It might be, early stopping that you might have. It might be some other parameters that you actually want to use as part of hyperparameter to create your particular model. It might be for XGBoost or for decision tree. It might be the depth of the tree. It might be how you're actually doing bagging and all that. And those are set before the tuning. And the result of that training is that it affects how the algorithms of the model parameters are done. And the model parameters are the result of the trials with which we actually use the hyperparameter. So for example, linear regression just could be the coefficients and plus the bias. For neural network, just could be the weights and the bias, and so on and so forth, which actually learn during the time of training as you go through the hyperparameter. So a concrete example of hyperparameter tuning would be a typical, very complicated classification problem that you might have in a neural network. And all the numbers that you actually see over here are your hyperparameter tuning. Right? These are all the numbers that you actually want to try out, different trials to find out what is the best classification problem, the optimal loss that you actually will have, and what's the optimal architecture that you actually have. You can do it just through trial and error. Now you can surmise and you can take this logical conclusion that your hyperparameter space can be rather huge, right? It can be really can explode, and as a result of that, there are some challenges. It's time consuming for one, because it can be costly. Your hyperparameter tuning parameter, if you have a very large hyperparameter space, can run from minutes to days to hours. And as a result of that, cloud computing is expensive. So your resources, especially if you're using GPUs for doing a lot of tensor computation, it's going to be expensive. So you want to make sure that your trials are efficient and they're at a lower cost and they're fault tolerant, right? So if you're using for a particular trial, you're running for 2 days, and all of a sudden something dies, do you start all over again, or you start from where it actually left off? So I think these are some of the challenges that you have to take into account when you're doing hyperparameter at scale. And RayTune sort of gives you a few strategies that allow you to be able to do that, because it has the sort of algorithms that come straight out of the box that gives you the ability to combine, easily swap in and out both the search algorithm type along with the scheduler to see which one I can actually use to get my best trial. And there are essentially 3 strategies. One, you use the exhaustive search, which most of you are familiar, and those are good for small exhaustive hyperparameter space. You got Bayesian optimization that is sort of more probabilistic and stochastic, is saying, okay, I'm going to figure out what was my previous one. If I had a better one, then I'm going to go ahead and continue with that. And the advanced scheduling is more about successive halving and early stopping and having frequent checkpoints to make sure. So if you look at the exhaustive search, that's probably the best one. Everybody has used that. If you're using scikit-run, you're going to create a particular grid search and you're going to have a random search. And they're easily parallelable because Ray can actually parallel each and every different combination, discrete combination of that and parallelize that. But they're very inefficient and expensive because you're not really looking at the result of the previous one to see whether it was a bad trial. You just keep on brute forcing all those. So that can be quite efficient, but they're very easily parallelizable. The second one, which is sort of more favorable, which is that you can actually use the Bayesian optimization to look at the previous combinations of how did the trial do. And you can sort of create a cluster of the good trials that you're going to select a combination of those using Bayesian processes, and you're going to chuck the other one into the bin and don't even think about it. And these kind of are inherently sequential, but at least they look at the history or they look at the previous trial to see if I really want to continue that. And recent literature, from what I read, is that there are some libraries that are already allowing you to do that in distributed methods such as HyperOpt, Noctuna, and Scikit Optimize and Nevergrad that support the Bayesian optimization on multiple machines rather than a single machine. So that's the second one. And the final one is the advanced scheduling. And the advanced scheduling is a combination of using ASHA algorithms or successive halving, where you fan out, right? You fan out all the different trials. And what happens at this point is that each and every rung of your trial is looked at by the main scheduler that we'll get into, that looks at, oh, this particular trial is really bad, I'm going to kill it, right? But I'm going to follow the next one. And he keeps on following the best one, the best rung that actually takes it all the way to the end. So this allows you to do early stopping and successive halving of your trials, and it minimizes the number of your hyperparameter space and uses your resources and time in a more efficient manner. So I think these are the three strategies that it allows you to do that. And how does it do that, right? If you look at the ray-tune sort of hyperparameter code, it's very simple, right? You need 3 steps. You're going to write your training function or your objective function just like you would write any particular function, say in Keras or in scikit-learn, or you're going to do it in XGBoost or in PyTorch. You're going to write your training function. Next thing you're going to do is you're going to specify your hyperparameter space that you actually want, and you're going to provide the training function in the tune.run. You want the number of samples you want, and then you're going to choose whether you want ASHA as your scheduler, and then when you want your search algorithm to use Optuna. And then you just do tune.run. And at this point, what will happen is that the driver process now is going to create an orchestrator that's going to do the tune.run. And the tune.run driver process is going to create all these worker processes, right? These worker processes will be launched across the entire cluster, and each will get a copy of your training function along with a slice of the trial that it actually is going to compute and do the hyperparameter purge. And this is actually done fanned out across that. Every now and then, they will report back metrics to the main orchestrator, which is actually running that as an actor, and it's going to report those particular metrics. And they will ascertain whether I want to do an early stopping based on my previous trial of that. If it is, then it's going to kill that, launch a new one, and continue doing that. And every now, often, and then, configurably, you can say, I want to go ahead and checkpoint everything I've done so far, and those checkpoints could be stored in the cloud somewhere. Because should something go wrong, as I said, it's important to this to be elastic and fault tolerant. I can now reload my checkpoint from a cloud storage and restore it back, and off I go back to the tracks. So this is sort of the tune underneath that uses the orchestration of worker node. Now, somebody asked me a question, what about if I'm using PyTorch? Well, if you're using actually distributed training over here, this particular trial function is going to be your PyTorch function. And the way it's going to communicate gradient is it's going to be using the PyTorch DTP protocol to exchange the gradients. We are sort of orchestrating at the higher level, so we can actually scale out across. So that's why that's the essence of hyperparameter optimization. So just to sum it up before I get into demo, I think we got a few minutes. Like I say, today, distributed computing is a necessity because of the foundational models that people are actually building, because of the pervasiveness of how ML has actually entered into our space, and that's sort of become a norm. The vision, obviously, of Ray is to sort of make distributed computing a lot easier, to provide you with the compute strata, so you can scale your Python applications or your ML applications, or write any distributed applications that you want at a particular scale by just using simple programming notions and simple programming APIs that you, as a Python programmer, are used to it, but you're just doing it in a distributed manner, in a very seamless manner where you don't worry about socket, you don't worry about where it's actually scheduled. All the hard part is actually done. You just write the particular code to do that. And like I said, you don't have to, be an expert in HPC. You really just need few primitives to be able to do that. And the libraries that we actually provide hide away all that from you, right? To do that. Just like, remember, I was trying to use the knowledge about Unix, right? If you're actually using a compiler, or if you're using the editor, or if you're using any of the tools which are built on top of Unix operating system, you're not writing fopen, and you're not writing, you're not scheduling, or you're not doing context switching. All that is taken care of by that. You're just using that as at a high level. So that is the essence. And obviously the whole idea is that we will be able to scale your workloads using Ray as the compute strata for you to be able to do that.
Jules?
Yes.
Can I ask a question here for someone?
Of course.
If it's not appropriate at this time, just let us know. How does RayTune HPO compare to other AutoML systems?
When you say AutoML, I mean, AutoML is like a zero code, right? So for example, if you look at PyCaret, PyCaret is a very popular AutoML toolkit. Underneath, it uses Ray to do automatically tuning your parameters, right? So you might say, go ahead and create a linear regression model for you, model for me. And by default, it will select some parameters, and then it will use underneath called RayTune to do that. GradeFlow is another one that actually uses the Lightning, PyTorch Lightning to do the AutoML for it. So AutoML can use RayTune to automatically go ahead and do the hyperparameter tuning for it. And the AutoML library can abstract away calling underneath how RayTune is actually used. So those are the examples of that. I think when you say comparing, over here, the RayTune is not automatically doing something for you, right? You're given a hyperparameter space. You tell them, here's my hyperparameter space. Here are the number of samples that I want, and I want you to go ahead and fan it out. Now, if I wanted to write an AutoML wrapper on top of that, then I could just hide away the tune and say, go ahead and create my linear regression model, and I'll have some default parameters, right? And then those default parameters can actually have my hyperparameter space, or I can read a hyperparameter space on some config file, and it will just do it automatically for me. So that's where the differentiation comes in. AutoML can and today does use RayTune for certain libraries such as PyCaret and GradeFlow and some of the other ones. I hope that answers the question.
Okay, thank you.
Mm-hmm. So if you want to get involved with Ray, just go to ray.io. We've got the GitHub. Give us a star. We love stars. We live in a galaxy full of stars, so we love stars. We have a Discuss forum that you can actually pose a lot of questions. Join us on Slack. We have a newsletter. Follow us on Twitter, and we follow you. I know it sounds dodgy, but that's the reality. And most important thing, guys, you guys all live in the Bay Area. We're having our first Ray Summit, in-person Ray Summit in San Francisco at the Hyatt Regency exactly a month from today. We have cut down the cost quite a bit because we want, given the economic circumstances, we want everybody living in the Bay Area want to know about Ray to attend. We have a packed schedule, great keynotes, training sessions as well. Just use my Damji25 discount code. You can actually either buy a bundle for 125 and attend one of the training. I'm teaching one of the training classes, or you can just attend the regular breakout sessions. So there is the link for you. Would love for you to actually have and attend to find out more about Ray, because there are companies who are actually using Ray. They're building infrastructures, they're building ML platforms. They have use cases that I had never heard about, how they're actually using it. One use case that really threw me off was, World Cup. I'm a big football or soccer fan, and I go to every World Cup, and there's one happening in Qatar in November. And one of the FIFA World Cup, along with the Qatar Institute, actually did a simulation using Ray and RLlib to find out what would be the worst case scenario to maintain and manage traffic, right? Because Qatar is a city-state, 20-mile radius of city. You got games happening at the same time. What happens if something goes wrong? So all these different scenarios that could possibly go wrong, and what would be the rewards that people would do and how they would actually simulate that was done using Ray and using our RLlib reinforcement learning to do the optimization of traffic and human traffic control and car traffic control. Just amazing. I've been to the World Cup and I know what's like in the bloody chaos, right? 3 hours before the game, it's massive human traffic cars all over the place. So this was an interesting use case. And there are going to be loads of use cases, right? How Instagram is using it, how Shopify is using it to build recommendation system, how they actually use Berkeley on top of that to use Ray. All these interesting use cases that people are using at massive scale. This is a place to find out. So please do come by, and if you see me, come and say hello. I'd love to have a beer with you and chat about how you're interested and how I can get you all started about Ray. Okay. Any more questions? I can get in the demo quickly.
I don't see any questions.
Okay. All right, brilliant. So I hope, can you see this?
Yes.
Okay, I hope the demo goes up with me. So what I'm going to do over here is I'm going to demonstrate you with three training loads that I talk about that you can actually do at scale. One is training, the other is hyperparameter tuning, and the third one is inference, right? And so the scenario is that I'm going to train something on my local machine or my on one node, and then I'm going to do the same thing on a distributed cluster that will scale, and you'll actually see the noticeable difference. I'm doing this on my Anyscale cluster. This is my Anyscale cluster that I actually created. I have a little dashboard that has 8 machines with 16 cores. So a lot of compute power, and let's actually do that. So I'm going to go ahead and I've created a data set that has 10 million rows. I have 40 features, and I'm doing a classification using two classes. I have some Parquet files that I actually created so that I can read it. I've created 3 different kinds of files so I can see and partition them. I got 300 megabyte just to test to see how my function is doing. I got 3 gigabyte files, and I have 11 gigabyte files, and we'll see how to do that. So the first thing I'm going to do is I'm going to use training function on an XGBoost, regular training with your default parameters that you actually use in XGBoost. I want to use the tree method. It's a logistic regression. This is my evaluation parameter for logic laws. And I'm just going to import my train function from XGBoost and typical stuff that you actually do. Define the files, create my training set, convert them into the D matrix representation, which is the efficient way of how XGBoost runs. And I'm going to create my training function. And I'll provide my number of rounds that I want, my parameters, and go ahead and create a particular function. So when I run this, so let's just define this particular function over here. And let's run this with 300 megabyte. So when I went 300 megabyte, just test to see, make sure my XGBoost function is working. When I do that, it doesn't take that long. 300 gigabyte is not that bad. Then I'm going to try that with 3 gigabyte using the train XGBoost. And when I use the 3 gigabyte file, you can actually see that when I ran this, it took me about 150 seconds on one particular node. Now what I'm going to do is I'm going to take the same 3 gigabyte file that I have, but I'm going to run it in a distributed manner using XGBoost on Ray, right? Now, XGBoost on Ray is a replacement for XGBoost Ray. And all it does is it uses the tracker, like I say, uses the tracker to launch all these particular workers. And each and every worker will have a data shard, which is combined, which is divided into partitions. And each and every worker will run on that particular shard. And every now and then, they will actually communicate using Rabbit and using tree reduce to coordinate the particular weights, right? The only difference between the one running on my local node using a single node XGBoost is I just import from XGBoost Ray these 3 arguments or these 3 parameters. Instead of creating a D matrix, I create a read matrix, which is going to be my distributed shards across my cluster. And I'm going to provide to the training XGBoost an argument, a class called RayParam, which is the level of parallelism that I want, right? So all the function is exactly the same. The only difference is that I'm using the Ray D matrix files, and I'm providing the amount of parallelism I want using RayParams, right? So when I actually run this across my cluster, I'm saying use 8 actors and 16 CPUs. It's going to use everything possible. So I'm now running this in a distributed manner, and it's going to run across the cluster. It'll train those using the default parameters that I have. It's going to use all the CPUs that I have, and it should actually just finish. If I go to my Ray cluster, I should actually see all these workers running. Wow, it's done. Okay. So this particular is running in a distributed manner. It's about 7 gigabytes. And it should take about 1/3 of the time it actually took for me to be able to do the tuning. I mean, do the parallelism on this particular machine. So this one here actually took me about 149 seconds with the same amount of particular file, just using one machine and just using whatever cores that I actually have. But this one is running in a distributed manner and running on. So what's happening over here is when the next load I'm going to do is the hyperparameter tuning. I think I was waiting for too long. I'll take any questions as we actually see this particular thing finishing. Do I have any questions in the Q&A?
Hey, Jules, I'll go ahead and ask one real quick. So there's a couple, like weights and biases tracks these things. And then SIGOPT does, hyperparameter tuning, right, with an optimization algorithm. How do you differentiate yourself, say, against SIGOPT?
I mean, I haven't done any benchmarks per se. We actually haven't done exactly any benchmarks, but it's okay. This is hyperparameter tuning on Optuna, and this is using RayTune. And the reason is that we can actually use those as part of the trials, right? So when we say I want to go and use search algorithm, I'll use Optuna, we can actually use Optuna over there. But to give you specific comparisons between Optuna and RayTune, no, we don't actually have those benchmarks. But as soon as we have, we'll definitely publish that. But the reason we probably don't have that because you can actually we integrated with Optuna and SIGOPT, right? So you can actually use SIGOPT to be able to do that. So if SIGOPT is faster, you can actually use that with Ray because all we're doing is we're just calling SIGOPT as part of it. So this is a bit odd. I think I have something going on my cluster. It should be taking this long. Any other question? Okay, so while this is running, keep on going. Now we can actually do the tuning, right? And as I said, when you're doing hyperparameter tuning, you're actually launching this across the clusters. And when I launch this across the clusters, you can actually see that it uses all the 140p CPUs across, creating the best hyperparameter trial that I actually got. And it took about 100 seconds. If I did that on a local machine, it would take me inordinately a long time to do that. Let's see, how does the code compare with TensorFlow, for example, tensor classes? Could 3 Windows workstations serve as array nodes? When you say Windows workstations, what do you mean? Are you talking about like Windows operating system? Or are you talking about Azure running VMs? Yes, a Windows workstation would actually require a VM because I don't think we run on Windows yet. We have a client that actually runs on Windows. Okay, which is better to do model train dendrites, neurons, or Spark or Ray? I don't know if I understand that question.
Yeah, that doesn't, to me, look like the kind of thing that you would really be using either one for?
Which is better model to train? I mean, if you're doing, if you're doing deep learning and a distributed deep learning using PyTorch, I would probably use Ray, not Spark, because of the level of support you actually have. If you had to do a distributed training on Spark, you probably end up using Horowod, which is another level of interaction. But over here, you're actually just using PyTorch DDP protocol to do your distributed training, and it's much more efficient that way. Are semaphores completely hidden? Yeah, obviously. I mean, if you're doing distributed computing, semaphores are actually part of the operating system. You don't actually create a semaphore itself. It does all the semaphore automatically for you. Okay, so when I did that, it actually took 11 seconds. You can see that the amount of time it took me to do on single machine was 146. Over here, this was about 10 times faster. Same thing with when you do actually an inference on a local machine, running those inference, it'll take you 11 seconds, whereas over here it just took me 9 seconds. So there is a huge difference in over here you took about 80 seconds, and over here you took 9 seconds, so 10 times, almost 10 times faster in doing inferencing. So we actually did 3 loads. We did the training, which allows you to do that in a distributed manner. We actually saw the significant difference in number of seconds. We did the hyperparameter tuning at scale using across all the nodes. And then we did the inference on the same 11 gigabyte on the local machine, and it took us about 11 seconds to do that. Whereas running inference using XGBoost on Ray, it cut down our time from 80 seconds to 9 seconds. Any further questions? So that was essentially the demo that I actually had. And like I said, here's my contact information. Just send me any mail that you actually have, jules@anyscale.com. If you go to, for example, ray.io, and the question was documentation. So I'll go over here and I do Ray train. I go train examples. And these are all the examples that we actually show how you can actually use PyTorch in a distributed manner, how you can use TensorFlow, how you can use Horowod, how you can actually use callback functions. Those are all integrated. For example, if you're doing experimentation with weights and biases, and you want to track all your tuning parameters and experimentation, just with MLflow and with weights and biases, you can actually do that. Here's an example how we actually use tune integration examples. There are some benchmarks over here that talk about PyTorch data transfer and auto pipeline. But so somebody asked me, how do you actually do the PyTorch example? Here's a whole list of it. If you go to the tune, same thing, the user guide, we actually give you an example exactly how to do this, right? Using resources to do your parallel distributed runs using on GPUs. All these examples, sorry, there's treasure trove of code over here that tells you how to do that. And there are more specific examples that are aimed towards different libraries and different frameworks that work with Ray. And you actually have all this code available to you. Okay, there was, is there a comparison doc? No, I already answered that question.
There's a question, can the Ray cluster include a mix of GPU nodes, TPU nodes, and CPU nodes?
Yes, I mean, right now, I'm not sure about the TPU because we don't have, but I'm sure we can actually use the GPU. Yes, you can actually create, if you're on AWS or if you're on Google, you can actually create, say, a head node or a cluster which has X amount of CPUs and X amount of GPUs. And that way, when you're actually creating a Ray actor or you're creating a Ray task and you say, I want this particular Ray actor to use a fraction of the GPUs, then you can actually do that. Yeah, you can do that. And if you go to, for example, of a cluster manager, you can actually use these launching clusters on any of these, AWS, Azure, GCP. Oh, Alien, this is something new. I didn't know that. Yeah, so there's tons of resources over here, tons of information how you actually do that. The only thing we can't really do that at a particular meetup is, you need the AWS cluster and you got to go ahead and launch the cluster and do that. But If you're using Anyscale, you can pretty much create any of these clusters that you can actually use very easily. So I don't have where you create a YAML file and worry about having the credentials. I'm just using Anyscale. I can create any of these clusters using the code itself right away.
Have you,
any more questions? Go ahead.
Have you worked with any external companies to help them implement RISELab in their business?
Yeah, I mean, there are two kinds of companies, right? We have companies which use Anyscale, and there are companies who use AWS. And I showed you in the particular slide, some of the companies who are actually already using the open source version of Ray, right? Who is using it? Loads of them who are actually using it. And these are, pretty much independent companies who actually know what they're actually doing, right? Now, companies, say, for example, like Shopify and Dendra or Riot are using sort of Anyscale version of Ray, whereby they're doing POCs and other stuff. There are lots of customers who are already doing POCs that I'm not at the liberty to talk about. But some of the ones which are on the website, you can actually find out on Anyscale whoever current customers are who are actually using
and
success stories.
You mean proof of concept?
Well, proof of concept are the ones who actually sort of still are considering, but some of these companies are already using it, right? So Dendra is already an Anyscale customer. Ikigai is already an Anyscale customer. Pathmind used to be, now they're actually moving more towards Amazon are using all these. So these are some of Anesthesia is already using Anyscale, and some of these are using open source. And there are a few who are going to be presenting at the Ray Summit who are using Anyscale at scale, and the other ones who are using open source at scale. So the ones that I'm not at the liberty to talk about are still using POC at a massive scale. But once we actually have them, then we'll be able to share that information.
Okay. Any other questions, folks?
But like I said, I mean, if you really want to find out and meet the community, how people are actually using it and how they're building things on top of Ray, right? So Predibase is another one who's actually using AutoML, and Ludwig underneath they're using Ray to orchestrate that. Uber is using XGBoost on Ray at a massive scale, right? Dendra is actually using Anyscale and Ray to do computer vision. They're really interesting use case, right? They are one of the ones that really piqued my curiosity because they use deforestation, right? So they have these drones in Australia that they run across the desert and identify areas which are being deforested, and they plant seeds and they use drone to track the growth of the particular deforestation. And they use the drones to actually take the images of that and then use the computer vision to do classification. And all that's driven by Ray in the back end and Anyscale to do that. Quite fascinating use case.
You had put up that page full of sample code and whatnot.
Yeah.
And is that easy to find?
Oh yeah. I mean, what I can do is I can probably I can share some of these links with you.
Okay.
Yeah, because if you just go to ray.io, right? If you just go to ray.io, as I did over here, docs.io, you'll see these things over here, right? So you go to docs.io, you'll get all this ML library. Click on any one of these, right? If you just click on train, you'll get train examples. You'll get user guide. Each of these actually have sample code that allow you to do that. If you go to tune, just pull down on tune. You will have user guide as examples. All these have code examples. You can just do cut and paste. Not only that, if you go to this particular examples, you can also sort of download the notebook, right? So I can actually go in and download the IPT. I can actually run that in the binder and in the Colab. So all these examples are there for you. You can just run them right there from your laptop or from your browser. And we have made a huge improvements in our documentation. And plus Plus, we are unraveling Ray 2.0 coming up, announcing in next week. We're releasing a pre-version of the Ray 2.0 that has loads and loads of improvement.
Okay, Yash, did you have anything more? Looks, I guess.
No, I think this has been really fantastic, Jules. Thank you so much for being available. I think we're really excited to, I'm going to at least try it out tomorrow on my AWS account and on my personal laptop. So let's see how it goes. By the way, as far as RISELabs is concerned, what's the next thing? Do you have any comments on that?
I mean, they're doing a lot of interesting research, right? I think one of the presenters, who's a student, PhD student of Dr. Stoica, is going to be presenting his work at Ray Summit called Sky Computing. So what's the next thing, right? Sky computing.
Well.
And sky computing is this whole notion about multi compute, because people, are not going to be just using one cloud. They're going to be using multiple clouds, right? To do different things. And sky computing is sort of the next way that abstracts away what cloud you're using. You have a particular workload that you want to execute, and they will use the BCP and a way to figure out where to actually execute that particular cloud. It's quite interesting. I read the paper. It's kind of academic, but I think it's the future, right? The same thing when Spark was being developed, people say, "Oh, it's all academic," and then look what's actually happened with Spark and Databricks. The same thing, Ray. Oh, it's an academic exercise, but now people are beginning to say, "Oh my goodness, right? I can actually do distributed computing. I don't have to have a PhD in understanding systems and how distributed computing work. I can do that pretty much easily by just writing Python code with some APIs that Ray allows you to facilitate that." And if you don't want to do that, you can just use the libraries that hide all those primitives away from you, and still be able to do your ML at scale.
Okay, fantastic. I know we're a little bit over time. I'll look at the monitor here, but thank you again. And folks, if that's all we have here, then if there are no more questions, then we'll go ahead and sign off. Thank you so much.
Okay, thanks a lot. I appreciate that. And I'll go ahead and send you the PDF so you can share it with the community. The slides, because it's got all the links in it. All right, cheers. Good night.
We'll post
thanks
it
for
on our
joining.
meetup as a link. I think that might be
okay. Right, I'll do that. All right, brilliant. Thank you.
Thank you.
Bye-bye.
Okay, good night, folks.
Good night.